Alright, gang, here we go. This is Physics, Unit 2, Chapter 3, Part 1. So we're talking about vectors. We just finished Unit 1. It's all downhill from here. It's nice, right? So here we go. We're going to be talking about vectors. So just to recap a little bit, up until this point, we've been talking about motion in one direction, right? We talked about what happens if a car or a person running or a dog moves to the right or left. We also talked about what happens when we throw a ball up into the air and it comes straight back down, right? We talked about dropping things, right? So on and so forth. So we talked about motion in one direction. That was pretty easy. We just took our equations, figured out our variables, plugged in, chugged, and that was about it. Now, with chapter 3, we're going to start moving on to vectors in 2 dimensions. So that means we're going to be thinking about moving in 2 things. So if you imagine you take like a cannon, right? Okay, there's my cannon. Okay, and it's on its stand. So we take a cannon and we're going to fire a cannonball. Well, the cannonball, the motion of it, it'll come up here, right? But then it'll start to come down. So the cannonball went up and it went to the right, right? It went this way, okay, this distance from here to here. But then it also went up and down again, right? So it also traveled in the y-axis. So it traveled in 2 dimensions. It traveled in the x and in the y. All right, so that's kind of what we're talking about now. We're going to talk about motion in 2 dimensions. So first, we need to establish vectors and establish what a vector is, what it tells us, how we can work with them. Okay, this is very, very, very important. So I need you to make sure you do all of the practice problems. All right, come in and ask for help. Watch this video several times, right? Make sure you understand vectors because they will apply through the rest of the year. This is very, very important stuff. All right. So there's 2 things, right? A scalar versus a vector. Scalars are things that you're used to working with, okay? It's a physical value that has magnitude, right? So 2 is a scalar, all right? So we've just got something we've counted, all right? And it's got a magnitude. Remember, when you hear magnitude in physics, right? You hear that word magnitude, you should think absolute value, okay? All right? Absolute value. So magnitude, how big it is. So it's got a bigness to it, but it doesn't have a direction. All right. So here's some examples. Remember we talked about speed, right? Speed doesn't have a direction. If you're going right or left or up or down, it doesn't matter what direction it is. Your speed's always the same. Or the volume. Okay, the number of pages in the textbook, so on and so forth. Those are all examples of scalars. Now, vectors are special. We've already talked about several vectors. We just haven't really specifically called them vectors. Okay, some vectors that you're used to talking about are displacement, right? Remember we talked about displacement? It matters if we go right or left. We represent it with a positive or negative, or up or down, positive up, negative down, all right? It matters how far we moved, the magnitude, but it also matters the direction. Same with velocity and acceleration. Okay, just a little note on notation here. Scalars are always represented in italics, and vectors are always bolded. All right, so this is when if you're reading the textbook, following along in the PowerPoint. All right, that's how they're represented. So scalars are italicized, vectors are bolded. In class, when you're actually doing problems, when I do them on the board or when you're doing them on your homework or a lab or quiz or an exam, okay, I want you to represent a vector by placing an arrow over the variable. So say our variable is x. Okay, you'd put an arrow over it to say that it's a vector, all right? Because it's hard to write things bolded and italicized when you're handwriting. Okay, so we just assume if we see a number or a variable, if it's by itself without an arrow, then it's a scalar, but with an arrow, it's a vector. All right. So here we go. So a vector, okay. When we're looking at a diagram, we use arrows, all right? So arrows, so we're going to use arrows with a little head on it like that, all right? So that's our arrow. And the arrow shows us the direction, all right? And then the length of it shows us the magnitude, all right? So the arrow shows the direction where it's pointing, and then it also shows us the magnitude. Okay, so here's some velocity vectors that are on these girls playing soccer, all right? They're both headed towards the soccer ball. I see that? They're both pointed at the soccer ball. But because the red arrow on the girl here is longer, okay, then that means this red girl is moving faster than the one in blue. Right? These are velocity vectors. Okay, they have the direction, they're pointing at the ball. They're both headed in the direction of the ball. But because the red girl is longer, it has a bigger magnitude. That means she's going faster. Okay? So in class, we did a little bit of a box demo. Remember, we took our box, all right? Okay, we'll call him Pete. Okay, Pete the box. All right, Pete the box. We take Pete the box, and remember, we pushed him one way, and he went down that way, and that was pretty cool. And then we said, all right, what if we take Pete the box? All right, we'll call him Pete, PTB. All right, Pete the box. All right, we take Pete the box, and we're going to push him another way, right? So he goes this way. All right, well, that's pretty cool. We can represent the displacement of Pete using vectors, right? So his displacement down was this way, his displacement that way was that way. All right, and then we took Pete the box and we pushed him in two directions at once, right? So we had PTB, and one person pushed down and the other person pushed to the side at the same time, and he went diagonally. Remember that? Okay, so we could combine. So when we pushed, you know, here, right? So I'll put a dashed line because it's not a vector. Okay, and we pushed here. All right. So when we pushed this and this, we ended up with a movement this way, right? And so remember, and we talked about how we could figure out what this movement would be by adding these two vectors together. So you imagine if we took this vector that's going down, all right, so I'll draw a line here. If we took this vector that was going down like this and then combined it with this vector going this way and it was going that way, then we end up with this guy here. This arrow here showed us the same movement as it was going on here. Okay, and then so this arrow that's going down into the side, this arrow, remember, has a special name. It's called the resultant. All right. Okay, so that's the resultant. It's the result of adding these two vectors together. All right, that's why we call it the resultant. And then we also said that we can reverse the order. So remember, we went down first and then went to the side. It doesn't really matter if we go to the side first, right, and then go down. We end up with the resultant. Okay, remember this guy's the resultant. That resultant is in this, it has the same magnitude, same size, and the same direction. All right, so it doesn't matter. All right. So when we add vectors together, we get this term. It's called the resultant. It's the result of adding our vectors. All right. Okay. So the resultant represents the sum of two or more vectors. So when we take a vector, we're adding them together, we get the resultant. Okay, there's two ways we're going to talk about graphing or figuring out the direction and magnitude of a resultant. The first way is the graphing. Now, graphing tends to be a pain in the neck because that means you have to have a graph paper, you need a ruler, you need a protractor, make sure you're getting all your angles just right. All right, so it kind of tends to be a pain in the neck, and then we'll talk about how to do it mathematically here in a second. Okay, so here's an example. So we've got a student, he's walking from his house to his friend's house, and then, so A is his house, B is his friend's house, and then he walks from his friend's house to school, from B back to the school, all right? So A is this path from his house to his friend's house, and then B is this path from his friend's house to the school, all right? And then, so therefore, his resultant, or the actual displacement, right? Because remember, the displacement is defined as the straight line between the beginning and the end point. Okay, so this was his beginning point here at home. This was his ending point here at school. So the resultant was the actual distance here. So in order to find this value, because we've got it graphed out, drawn, we can figure out that all we have to do is measure this and figure out exactly what his displacement was. So graphing it works that way, all right? Now, a couple of rules about moving our vectors, okay? We can move our vectors parallel to themselves in the diagram. So that means, like, if our vector is pointed down and it's this big, we can slide it, we can translate it around the page. So we can move it left, right, up, or down, or diagonally. We just always need to make sure that wherever we end up, it's parallel to the way it started. So if I move it over here, I need to make sure it's pointed in the same direction. All right, that's what it means by moving parallel. All right. When we draw them, we always draw vectors tip to tail. Okay, so we always draw them. Remember my other vector, I went like this. So this was the tip of the one right here. This was the tail, so you're going to do tip to tail. You never, ever, ever, when you're adding your vectors, do them like this. This is no good. Bad news. You also, that's tip to tip, and you also never do tail to tail, right? So it would look something like that. That's also bad news. No good. Only tip to tail, all right? All right. From the tail of the first vector, and then so the resultant is the tail of the first to the tip of the last. Tail of the first to the tip of the last. So if we have a, a vector addition, and it looks something like this, and then we jump up. Okay, the resultant vector would be from here, right? That's the tail of the first to the tip of the last, which would be here. So the resultant vector would be this guy right here. All right. So that would be the resultant. All right. Okay. So let's imagine a toy car. We're sitting on the second level in an airport, and a toy car is moving 0.8 meters per second across a walkway that moves at 1.5 meters per second. We want to determine what the car's resultant velocity will look like from our point of view. All right, so let's draw some of our vectors here. So we've got, it's moving 0.8 meters per second. All right, so that means we'll go here. We'll say this guy's 0.80 meters per second. All right, and then he's got another walkway. The walkway it's on is moving at 1.5 meters per second. Notice that their signs are the same. They're both positive. That means they're going in the same direction. So we're going this way, and this is 1.5 meters per second. Now notice that I drew this line roughly twice as big as the 0.8. And that's because the magnitude is about twice as big. Remember, the length of our vector represents the magnitude. So we have 0.8 meters per second, 1.5 meters per second. So it's about twice as big, so it needs to be about twice as long. All right, now we need to figure out what the resultant vector velocity looks like. Well, in order to do that, we're going to add our vectors together. So let's redraw them. So we've got our 0.8. All right, so this is our 0.8 vector. All right, and then we've got our 1.5 vector. All right, so this is our 1.5 meters per second vector. Here's our meters per second. So therefore, our resultant vector would be from the tail of the first to the tip of the last. So I'll just redraw it right here. So that's the tail of the first. We go down here to the tip of the last. All right, and then what would be the length of this? Well, it would just be these two guys added together. All right, so this would be 2.3 meters per second. Isn't that slick? All right, so this kind of leads us into what we would do for calculating our resultant vector mathematically. So we've done it with a graph. All right, now we're going to do it mathematically. All right, so here's some math rules to keep in mind. Okay, vectors can be moved parallel to themselves, so the same rule as graphing. Vectors can be added in any order. Now remember when we did the box diagram way over here, down here at the bottom, we took, remember this over here, we did it both times. One time we did it where we went down first and then over, and we got that resultant. And the other time when we went over first and then down, notice we got the exact same resultant. Okay, all right. If for some reason we need to subtract a vector, we add its opposite. And by opposite, we mean the negative. Okay. All right, opposite, we mean the negative. All right, multiplying or dividing a vector by scalars results in vectors. So if for some reason we need to multiply or divide by a scalar, we still have a vector at the end. Okay. So when we're doing vector operations, we're always going to put it on an xy coordinate because we're already used to working that way. It makes life super easy. Okay, so we're going to use an xy coordinate system. All right. And then after we have them on the xy coordinate system, we can use the Pythagorean theorem, right, and tangent functions to add the vectors together. All right, super easy. Okay, so for example, so here's an airplane. I almost cut a car. Here's our airplane. Okay, it's going northeast, right? There's our north and there's our east. It's going northeast at 300 meters per second. Okay. We can redraw this so we can work with it mathematically on an xy coordinate, right? So we've got our airplane. It's 300 meters per second, so it's got the same magnitude, but it's at 45 degrees. So this angle right here is 45. Notice that we translated the northeast to 45 degrees, okay? All right. So go ahead and pause it and take a gander at these. Make sure you memorize them, all right? So practice time. All right, so let's do this. So we got 12 kilometers east plus 9 kilometers east. Well, this is very similar to the car. Okay, we go 12 kilometers east, 9 kilometers east. Yeah, I didn't do a great job making these different sizes, did I? And then 9 kilometers. So our resultant would have to be 21 kilometers east. All right, did we get it right? You betcha. 21 kilometers east. All right, how about this guy? So we go 12 kilometers east. All right, so 12 kilometers east. And then, then we go 9 kilometers west, so that's back this way. Okay, 9 kilometers west. So our resultant will be this distance right here, right? So this is our resultant, so that's got to be 3 kilometers, but we're still going to be going to the east, right? 3 kilometers east. All right, now life gets more exciting. We're going 12 kilometers east, so that's these guys so far. All right, 12 kilometers east, 9 kilometers south. All right, so we're going 12 kilometers east, so we got our 12, and we're going 9 kilometers south. All right, so then we go 9. So our resultant is going to be tail of the first to tip of the last, so our resultant is going to be this guy right here. Okay. All right, so now we have to figure out, remember, if we want the vector, we need to figure out the magnitude and the direction. All right, so the magnitude, we can use the Pythagorean theorem. Remember, the Pythagorean theorem is c squared equals a squared plus b squared. Okay. All right, so c would equal the square root of a squared, which is 12, so that's 144, and then 9 squared, which is 81. All right, 3, 4, 5 triangle, right? Yeah, so this should be 15. Let me double check just so I don't look like an idiot. So 144 plus 81, yeah, 225, and the square root of 225 is 15. Nailed it. All right, so that's the magnitude. So our magnitude is 15 kilometers, okay? And now we need a direction, okay? So it's not a pure 45, right? It's kind of a slant-eyed guy. If this was both 9, we'd know we'd have a 45-degree angle, but it's not quite. So now we need to use our tangent function, okay? All right, I'll put 15 just so it looks complete. All right, so now we need to use our tangent function. Remember, tangent of theta is equal to opposite over adjacent. So opposite over adjacent, all right, so but we need this guy here. We need that theta value. So theta is equal to the inverse tangent, okay, of opposite over adjacent, all right? So that means theta is equal to the inverse tangent of, the opposite is 9, and the adjacent is 12. So our theta would be equal to, say, second tangent, 9 divided by 12, and I got 36.87. All right, how many sig figs? Well, it looks like just one, but we'll just do 30. Let's say 37. All right, 37 degrees. All right, so this would be 37 degrees. All right, now we got to think about this. Okay, so this is where it gets a little tricky. So we've got, so if we're on an XY coordinate system like this, and our guy is coming off this way, and this is 37, right? So that means our vector is 37 degrees south of east. So I'll say south of east, right? Because it's 30, so we've got east, right? And we're 37 degrees south of that, all right? And look, that's what I got before, so that's good, all right? Now let's try this one. 12 kilometers east, 8 kilometers north. Let's try another one, okay? All right, so this is going to be very simple. You could pause the video and try it on your own, okay? Here we go. So 12 kilometers east. So we go east, 12, and then 8 north. So we go 8 north, all right? And so our resultant vector is going to be this guy here, all right? So that means the magnitude is going to be the square root of 144 plus 8 squared. All right, so I got 14.4. All right, so that's my magnitude, 14.4 kilometers. And then I can use this exact same formula right here because I already got it once. So my theta is equal to tangent inverse of opposite over adjacent, and I want this value right here, right? So my opposite is 8, and my tangent, my adjacent is 12. So my theta has to be equal to the inverse tangent of 8 divided by 12. And I got 48.11. All right, so we'll just call it 48 degrees. All right, and then we have to think about, so we're at 14.4 kilometers. And so now, so we think about where we are on a graph here. So if this is our graph, we know that our resultant vector is coming up like this. So that means we're going to be north of east. All right, so I forgot the degrees. 48 degrees north of east. All right. Oh no, what did I do wrong? All right. Tangent of 8 twelfths. 12 east, 8 north. tangent 40. I think I got the wrong answer earlier. It's got to be. All right, forget this noise. Yeah. 8 over 12. So 8 north. So that's my. Yeah. All right. It's got to be 48 degrees. Props for you that caught that before I got there. Okay. Resolving vectors into components. All right. So now that's just this little bit, and this is probably the most important part of this whole thing. All right. So zone in here. All right. So sine and cosine. We use tangent. Make sure you have your sine and cosine memorized. All right. Okay. So resolving vectors, it works opposite of vector addition. All right, so it's kind of the opposite of it. So we resolve our vector into the x and y components. So here we've got the velocity of an airplane, and it's going 95 kilometers per hour north of east. Right, it's east, and we're 20 degrees north of it. And we need to figure out the x and y components. So we need to know. So now we've got the resultant, and we want to know the x value and the y value that made up that resultant vector. All right, so let's figure out the the two values for these guys. Okay, so we're going to use sine and cosine. So we know that sine of theta is equal to opposite over hypotenuse, right? So it's opposite over hypotenuse. Okay, so so that means our opposite in this case is our v sub y. So our hypotenuse times our sine theta should be equal to our opposite, which is equal to our v sub y. Okay, so in order to get our v sub y, we just say, well, our hypotenuse is 95. We'll multiply it by sine of 20. All right, so we'll say 95 times sine of 20. All right, we get 32.5. 32.5, so that's the y value is 32.5. Okay, and then to get cosine, well, we know our v sub x is going to be the same thing, except that we're going to use cosine instead. So it would be hypotenuse times cosine of 20. Right, so our hypotenuse is 95 times the cosine of 20. All right, so our v sub x is 95 times the cosine of 20. We get 89.3. Okay, 9.3. So that means this guy is equal to 89.3 kilometers per hour. Kilometers per hour. Now we could check our answers by just using the Pythagorean theorem. So if we take 89.3 and we square it and we add it to 32.5 and we square that and take the square root of the answer, we should get something close to 95. I got 95.00276601. That's pretty close to 95. All right. So there's the answers that I got earlier. Thank goodness I did that one right. Okay. Now, here's where the rubber meets the road. Very rarely do we have perpendicular vectors, all right, that we're trying to add. So what we have to do is we have to be able to combine these vectors into and find their resultant. So here we've got two different displacements. We have displacement 1 that's kind of, shaped like this, and then we've got displacement 2 that's shaped like this. Now, in order to find the resultant, mathematically, what we have to do is go back to D1 and D2 themselves and separate them into their individual x and y components. Okay, and these are called resolving, and that's the special term. They're resolving the vectors into their x and y components. And these are the steps. So take a second and look at this. So we resolve each vector into the x and y components. All right, so we need the x and the y of these. Once we've done that, we'll use sine and cosine in order to do that. All right, once we've done that, we're going to add the x components. So look, we've got the x1, and then we've got the x2, so it's all the way out here. And then we add the y components. Here's our y1 and our y2, and we've added these. And now we can treat them as perpendicular vectors, right? Because now that's a right angle because we made it that way, because it's all x and all y. All right, so now this resultant is going to be equal to the resultant that we got when we added d1 and d2 directly together. All right, so that's the power of resolving those vectors. So let's do this one here together. All right, so a camper walks 4.5 kilometers at 45 degrees north of east, then walks 4.5 kilometers due south. Find the camper's total displacement. All right, so let's see. So we've got our xy coordinate. All right, look at that. Got our xy coordinate. All right, oh, let's change our color here. What do you think? What color oh, let's do blue. All right, so let's see, 4.5 kilometers north of east. So so we got 4.5 kilometers, so we'll go this way. We'll say it's 4.5, all right? And it's 45 degrees north of east. So there's our east, and there's our north, so we're north of east, so that's 45 degrees, all right? So 45 degrees. Then, so we walked that way, then he walked 4.5 kilometers due south, all right? So now we have to come back down straight south 45 kilometers, all right? 4.5 kilometers. All right, so that means he went down this way some amount, 4.5 kilometers. Okay. Now these two magnitudes need to be equal to each other. Notice how this line, because it went straight down, went past the x equals, or the y equals 0 value. All right, so that means our resultant vector, look at me getting all fancy, here we go, the resultant vector is going to be some value, right? Oh my goodness, I suck at drawing lines on this stupid thing. All right, the resultant vector is going to be something that's like this. That's going to be my resultant. All right, so in order to get these, notice how that this is not a right triangle. All right, and we don't have stuff to work with. So we got to be a little creative. We've got to follow through these steps that we had before. So we need to resolve our two vectors into their x and y components. All right, so this first guy, all right, we'll call him, we'll call this vector 1, okay? So let's see. So and these are distances, so we'll call it d sub x1, all right? So that's the x component of the first one here. So let's draw this guy out. So we got, we're going to make our triangle here, right? So this guy is a 4.5, and this angle is 45, all right? Which is nice, so that means we've got an isosceles triangle, right? Because this is that, and so that means that has to be 45. So we know that these two values are going to have to be equal to each other. So maybe I should redraw this to make it a little bit more accurate. So we got 45, all right? I failed again, didn't I? Yeah, I failed. Anyway, so here's our 4.5, and then so this and this, these are both going to be 45, right? And this is going to be like that. So that means these guys have to be equal to each other. Okay, so that's nice. So that means we only have to solve it once. All right, so if we want to find the length of this side, we can use cosine or sine. If we base it off this angle, well, we know then, and we want to find that one, so we know that cosine of theta is equal to adjacent over hypotenuse, right? And this is our adjacent, so we want to find our adjacent. So that means our adjacent, okay, and that's also equal to our d sub x1, right, is equal to our hypotenuse, all right, hypotenuse times cosine of 45. All right, and the hypotenuse is 4.5, so we take 4.5 times the cosine of 45, all right? 4.5 times the cosine of 45, we get 3.18, all right? Now, if you don't believe me from what we did before, all right, so that's got to be 3.18. Remember, we already decided that our guy was an isosceles triangle, right? So we don't have to do it again, right, with sine, but we certainly could. So, but it would be the exact same math. It would just be 4.5, but instead of sine, we'd use, or cosine, we'd use sine. So sine of 45. Sure enough, we get 3.1819. Same exact number. All right. Now to double check ourselves, right? Maybe I should write this as, so that means the d sub y1 is also equal to 3.18 kilometers. Now to double check ourselves, we can use Pythagorean theorem and make sure that these numbers add up. So this number is 3.18, and this number is also 3.18. So if we take 3.18 squared and then add it to ourselves, square it again, and then take the square root of that, we should get something really close to 4.5. I got exactly 4.5. So nice, math still works. All right, so that's the resultant of, or that's the x and y components of our first vector, the 4.5 at a 45 degrees north of east. All right, so this was our first vector here, 4.5 kilometers 45 degrees north of east. So that's our first one. Now we got to do this other one, 4.5 kilometers due south. So let's do it right here. So 4.5 kilometers due south. So that means we go straight down south, and it's 4.5 kilometers. Now let's think about this for a second. All right, we always have to use the x and y coordinate as our backbones to our triangle, and like the vector has to be the hypotenuse. Well, it so happens that the vector is the same, is parallel to our y-axis, right? So that means that the x value d sub x2, well, there is no d sub x2. It has to equal 0 because it's straight up and down. It didn't go left or right at all. Okay, we can't draw a triangle off that because we only have one line. Okay, all right, so that's no good. So it's d sub x2. So that means there's no math to do for d sub y2. It's all 4.5, so it's 4.5 kilometers. All right, cool. So now we can take our d sub x2, d sub y1. So we've got our d sub x2, or d sub x1 is 3.18 kilometers. All right, so 3.18. All right, and then our d sub x2 is 0, so plus 0. All right, that's easy. Now d sub y1 is 3.18, so it goes down 3.18. All right. Oh, I'm sorry. All right. I'm sorry. So this should be a negative value. There you go. So this makes, and this guy should also be, so this would be a positive 3.18. All right, here we go. I got myself confuzzled for a second. Here we go. All right, so I need a little bit more room. All right, so here we go. We're going to add these. Here it is. So we're going to add these guys. So there's our 3.18. All right, going to the right. That's our d sub x1. All right, then our d sub x2, or d sub x2 is 0. Okay, our d sub y1 is 3.18, right? But it's this vector right here, right? Because we have this vector here that goes like this, and we got this vector here that goes like this, and so it's a positive value, so it's 3.18 this way. All right. Oh my goodness, so it's 3.18 this guy, right? And then we go down, so d sub that's negative 4.5, so then we go down negative 4.5 from that spot. So first we have to think to ourselves, all right, what's this value here that we're going to end up down south? Well, that's going to be 3.18 minus 4.5. Okay, so this hypotenuse is 3.18 minus 4.5 is negative 1.32. So really, our triangle is going to look something like this, right? So we got 3.18 and then 1.32, and so our resultant vector is going to be pointing down this way. Okay, all right. Now to find our resultant, now we're back to the regular old vector addition. So we take 3.18 squared plus 1.32 squared, and then we're going to take the square root of that value there, and we got 3.443. All right, so that's the magnitude, which is 3.4 kilometers. All right, then, so that's only half our answer, right? That's just the magnitude of resultant. We need to know this angle right there. All right, so we're going to use tangent. So we already decided that theta is equal to the inverse tangent of opposite over adjacent. All right, so in this case, our opposite is 1.32. All right, and our adjacent is 3.18. So that means our theta is equal to the inverse tangent of 1.32 divided by 3.18. All right, and I got 22.54 degrees. All right, it looks like before I just rounded it to 2, which makes sense because we only have 2 sig figs. All right, so it'd be 22 degrees south of east, and we're south of east because remember we're down here, this is our east, and we're just south of it by 22 degrees. All right, so that's vectors. Do lots and lots of practice. This is very, very important stuff. This it's super complicated. It's not easy. All right, so you're gonna have to do lots of practice. It does involve geometry and a little bit of algebra 2 and a little bit of trigonometry, so on and so forth. All right, do your practice. Come and see me if you have questions, and I'll see you later.